Hello, everyone. This is Dr. White back again with the fourth and probably final screencast in our series on Chapter 1, Sections 3 and 4 of Open Intro Statistics. So here's where I've promised to give you another example of an experiment, and this time a real one, that was actually done at Georgetown College, and will not only describe the experiment and its design, but show you the data that resulted from the experiment, and we'll analyze that data all the way through to the inferential question of whether there's causation involved. So, question about spending habits. I want you to take a look at this question here. Say that you've purchased a $30 ticket to see a rock concert in Rupp Arena. When you arrive at the arena on the night of the performance, you find that you have lost the ticket. You don't have a receipt, and you forgot, whatever URL on your iPhone might lead you to some proof that you've already bought this ticket. So it's not going to be possible to see the concert unless you purchase another ticket. You got credit cards and things like that, so you could purchase the ticket. Would you purchase the ticket? And you just circle your answer yes or no. Okay, so that's a question about your spending habits, I guess. How conservative are you with money? Here's another question. You plan to see a rock concert in Rupp Arena. Tickets for the performance are $30. When you arrive at the arena on the night of the performance, you find that you've lost two bills from your purse or wallet, a 10 and a 20. Would you buy the ticket anyway? Assume you got a credit card and things like that, so you could use that instead of the cash. Circle your answer below, yes or no. So, let's think about this. When you process it through, either way, you've lost $30. In the first scenario, $30 went out of your wallet or your bank account or whatever, and into a ticket. And then that ticket left your wallet or purse and fell under the street somewhere. But the result is that you lost $30. And the question is, would you spend another $30 to see this concert? And in the second scenario here, you haven't bought the ticket yet, you're planning to, and you found that $30 has gone out of your wallet or purse onto the street somewhere. So in this scenario, you're also out $30. You've lost $30, and the question is whether you'll spend another $30 to see the concert. So if the amount of money that you lost is all that matters to the decision about whether to see the concert, then a person would answer either question the same way. A person who is kind of willing to spend money would say yes, whichever question she were asked. A person who's less willing to spend money would say no to whichever question she was asked. If money is all that affects our thinking about spending in situations like this. But could it be that our decisions about money are based not only on the monetary amount that's at stake, but also on the circumstances in which the money was lost? Could that be? Could it be that there are people out there who would have answered yes to one question and no to other, and people who would have answered no to the first question and yes to the other, rather than the world being full of yes people or no people? Are there people out there who are influenced by other aspects of the situation than just the money amounts? And examining this idea, this is something that economists do. There's an economist called behavioral economists, and they want to see if our notions and decisions around financial matters are just purely about the money, or if there's other possibly non-rational factors that go into our thinking. Um, and so one way that we could examine the question for ourselves is to do an experiment, and such an experiment was done at Georgetown College a number of years ago. We got 267 people to be in the experiment. They didn't actually know they were in the experiment. They were just students in classes, and instructors had given some of us permission to hand out survey forms at the beginning of the class. And so students were just thought they were filling out survey forms. And one of the questions on the form was, this concert scenario. Now, unknown to the students, some forms had the lost ticket scenario question. This first one here. And other forms had the lost money scenario question on them. This second form that you see here. About half of each. And it was a matter of chance which student got which form. And the students did not know until after the survey that there were two versions of the question. For all they knew when they were filling out the survey, they thought they were just being quizzed about like how conservative they were with money. They had no idea that they were really being quizzed about whether the way you lose the money affects your decision about spending more money. So they didn't know it, but they were part of an experiment, a randomized, blinded experiment. You see, it's an experiment because there's an explanatory variable here. Which form you're looking at, which way you're asked the question. And the value of that variable is being chosen by the researchers when they hand the forms out to you. It's randomized because they're handing it out by chance. It's a matter of chance which student gets which form. And it's blinded because the subjects in the experiments, the students who were filling out the questions, did not know what treatment group they were in. In fact, they didn't even know they were in treatment groups at all. So the data from this experiment is preserved in a data set in the package TigerStats. So you can learn about it with help attitudes and view attitudes. The name of the data set is attitudes. Let's go ahead and go to RStudio and copy, paste in, and run those two commands. And so if you read the help file, you'll learn about all the variables in the data set, and you'll also get some information near the bottom about this concert scenario situation. That's what we've already seen here on the slides, the two versions of the question. And in the view, you got the actual data. Every row here is a student. And the survey form had a lot of questions for the student. For example, the students were asked what race. They were asked, what year you are, freshman, sophomore, so on, what sex you are, what type of major you would like to pursue at Georgetown. And there were several other questions they were asked. And then they were asked the spending habits question. And the variable cons.situation here, cons is short for concert, that describes the scenario that the question presents. And you could either be in the lost.ticket scenario or the lost.money scenario. And the cons.decision variable that you see here, that's the response variable in the study. That's the answer that the student gave. If they wrote down yes, then we write by here. And if they wrote down no, then we have not dot by. Okay? So remember, we've got this research question. Does the situation that you are put in affect your decision to buy a ticket? And what we're looking for here is whether there's an association between two categorical variables. the categorical variable const decision, or const situation, the explanatory variable, and the categorical variable const decision, it's the response variable. And so in some R code that you'll learn more about in a subsequent chapter, you can use the tally function. And you run this code, you'll get this in the console. So let's just go ahead and see if we do it. There it is. So without going into detail at this point, how this code is getting exactly this result, let's just look at the table and see what we see. We see that there was a total of 130 people who got a form that said you've lost the money out of your wallet. And there's 138 people who got a form that said you've lost a ticket that you previously purchased. And the majority of people who lost money, pretty solid majority, 106 out of 130, said that they would buy, a ticket anyway. And just a very slim majority of people who lost a previously purchased ticket said that they would buy another ticket. So that looks like a big difference, but it is kind of hard to work with just the numbers, especially when the two group sizes are not the same. You should really compare percentages within each group instead. And so there's another version of the call to the tally function that you can run. It adds this little thing on the bottom, format equals quote %. Again, we'll learn all this more formally in another chapter. But if you were to run this code in RStudio, copy it all the way down to the closing parenthesis, paste it into RStudio and run, then you get the same stuff turned into column percents. And so there's a total of 100% people in the lost money column, but 81% said they would, yes, buy a ticket. And for the people who lost a previous ticket, only about 50% said that they would buy a ticket. In fact, that's a difference. 81.5 minus 50.7%. It's a difference of about 30.81% in the buy rate. So in this data we've got here, people were more likely by 30% to be willing to spend the $30 if they were in the lost money situation. That's a pretty big difference, it looks like. By the way, there's a quick way to calculate that using R. You can use the divprop function. And if you call it in this way, then it'll subtract the two percentages. And what it does is it actually works on the not by and minus, it works on the not by row of this table. And so it's this row right here that it actually works on. And it does 18.4 minus 49.2. And that gives you the negative 30.81%. So that's why that shows up in the console if you give it a try in RStudio. So this big difference is pretty interesting, considering that in both scenarios, one has lost the same amount of money. And like we had pointed out, if people make decisions just on the basis of hard money finances, they should be making the same purchase decision in either situation. So I would kind of expect that the percentage who say buy in both groups should have been about the same instead of there being this 30% difference. So I'm wondering, does this experiment provide strong evidence that the situation a person is put in has an effect on their decision to spend the money? Or is it just reasonable to believe that this 30.81% difference just arose from chance variation in which subjects got which survey form? Maybe just by chance, people who are conservative with money and don't want to spend a lot of money and tend to say no to the question however it's presented to them, just happen to get into the lost ticket. group. And that's why the percent was so low in the lost ticket group. And people are more liberal with spending money, maybe just happened to get into the lost money group, and that's why the percent was higher there. Could it be that that's what was happening? After all, it's a randomized experiment. It's chance who gets performed. Could it be, just by chance, that the two groups ended up looking really different in terms of the kinds of people who were in them? So that's the issue here. And to kind of look forward to some future chapters, let's introduce some terminology around inferential questions like this, where you're inferring from the data back to maybe a pattern that's out there in the real world. Let's state two hypotheses. First, what we call a null hypothesis, H sub 0. There's no relationship between the concert situation and concert decision. No association at all. Just chance in which people got which forms. Alternative hypothesis, there is a relationship between concert situation and concert decision. The difference of 30.81% is too big to be explained by chance variation in who got which form randomly. So when you're in this situation with these two competing hypotheses, you're doing what we call a test of significance. So just like with the dolphin communication inferential situation where we've got data and we're wondering if the data shows strong evidence that Buzz had a better than 50% chance of figuring out the right button to push. In that situation, we needed to find what's the probability, if he's just a random guesser, that he would get 15 on 16 right. Well, same kind of question here. If the H naught is true, if there really is no relationship between the way you're asked the question and the type of response you give, then what's the probability of getting a difference of 30.81% or more like what we got in this experiment? So again, the term for that we learned back in dolphin communication is p-value. This probability that we're looking for is a p-value. And how do we find that p-value? And I have a terrible error in the slides, which I will correct when you get to look at them. Because I'm like referring to a situation that was for some other slides. So bear with me here. You could repeat the experiment again and again physically. Like you could go and find 268, people whose decision ignore the word managers, 268 people whose decision is not going to be affected by which question they got asked. So I don't know how you would ever know that you have people like this, but if you could find such people, then you could repeat the experiment many times on them. And so you would be doing the experiment in a situation where everybody is either a yes to both types of question or no to both types of question person. And so you could repeat the experiment a lot of times, and you could keep track of the difference in percentages each time. And you would just find what portion of times did the difference turn out to be at least 30.81% that we got. And that portion would be your p-value. But this is just not practical. I mean, we'll just never know this kind of thing about people, that they're either a yes person or a no person. And it would be ridiculously expensive to physically repeat the experiment a lot of times. So we're just not going to do that. So here's our little clever idea to get around this. We're just going to suppose, for the sake of argument, that the null hypothesis is right, temporarily. It's temporary supposition. So we're supposing that the situation that a person is put in doesn't have any effect on the decision they make about whether or not to spend money. Then, each person would have said yes to both questions. They would buy. no matter which scenario, or they would say no, they would not buy. And so everybody's decision would be the same no matter which form. It would be either buy or not buy. And so actually repeating the experiment on them, if you could repeat it, you know, it it wouldn't cause anybody's actual answer to change. You know, like if I were in the experiment the first time and you gave me the lost ticket form and I said no, and then you like repeated the experiment on me and this time I got the lost money form, I still say no. You know, my decision wouldn't change. And this little insight leads us to the realization that we don't have to physically repeat the experiment on real people at all. All we got to do is take our data, where every row in the data is a person that was in the experiment. And we can leave the const decision row alone. But we can take that we can leave the const decision column alone. And we can take the const situation column and just shuffle around the values in it. And that would be like repeating the experiment again. Look back in our studio. Here are people. You know, each person, each row is a person. Their response is here, const decision. We're going to leave that alone. But what we could do is we make the computer shuffle around the values here in this const decision, in this const situation column. Switch them around. So some of the lost tickets, you know, they become lost monies, and some of the lost monies become lost tickets. That would be like handing the forms out again, randomly to the people. So you can actually make the computer do this. It involves some R code that you're not going to have to learn for tests or anything, but you'll need to run it here. This R code is going to create a little data table where you have shuffled the const situation values, but left the const decision alone. And we'll only show those two variables, the const decision and const situation. And that little data frame is going to be called simulated. Here, let's go ahead and create it. So I'm going to copy this code. I'm going to head over to RStudio, paste it in, and look at that. Simulated shows up in my global environment here. It's 206 observations of two variables. Let me press this button. And now it shows me that data table. And so the same like people are here, same 268 rows. And down the const decision is exactly what there was before, but the const decision, the const situation has been randomly shuffled. I mean, take a look at the first few values: lost ticket, lost money, lost money, lost money, lost ticket. Okay, and look over at attitudes here: lost ticket, lost money, lost ticket, lost ticket. That's not the same. They've been shuffled. And if you did this code yourself and you looked and took a view, you know, then you would see some different shuffling in that first column. But that's like repeating the experiment again. And so this slide here just shows you the first few rows of one of these shufflings, just kind of for the record. But what you can do now is you can make a tally based on that simulation. So this tally function here is still trying to tally up the counts for the situations and the decisions, but it's based on the simulated data table, not the attitudes data table. And so, like, you can run it here in RStudio, and you'll get a tally that pertains to the simulated table that you just made. Now, what I've got here is a tally based on the simulated table that I made when I made these slides. And so it's not going to be the same as the one you see, but I bet the results would be pretty similar. If you look at these numbers, looks like a majority of the lost money people are buying, and a majority of the lost ticket people are buying, and it looks like about the same kind of majority. It's hard to tell though without percentages. So why not just try your tally again, but with the format equals percent down there on the bottom. And if you try that over in RStudio, you'll get your percent table. I've got it tried here, and when I look, there's a 57% who said they'd buy if they lost money, and a 73% who said they'd buy if they lost a ticket. And that's actually a fairly big difference. 73 minus 57 is about a 20. No, it's about a 16% difference. Yeah, 15.49% is the difference if you try out diffproc. So actually, here's some code that's going to do all of that at once. It takes the original data, it shuffles the concert situation, and it calculates the difference in percentages. So it doesn't even like show you a table. It's just going to calculate the difference in percentages. So I'm going to try that over in RStudio down here at the bottom. And I'll run that code. Okay, I got a 0.024, a minus 0.024, so that's a negative 2.4%. Let me try it again. So I shuffle again. It's like randomly handing out the forms again to these people. Oh, that's about a less than a 1% difference. Try again. That's about a 0.5% difference. That's about a 2% difference. About a 2% difference. About an 8% difference. And you could go on like this. And I suggest that you just try that code a number of times. You can very quickly get it again and again just by doing the up arrow with RStudio. Just go to the up arrow on your keyboard and you get your command back again, and then press the return key and it runs that command. And so you can very quickly watch it go by, and the numbers will change because each time it's a different random shuffling of the values in constant situations, like doing the experiment randomly again and again. But and so you'll get different percentage differences. And just like see, did you ever get as much as a 31% difference? I haven't gotten that so far. So I'm starting to suspect that if the H0 is true, if concert situation has nothing to do with concert decision, then the chance of getting a difference of 30.81% or more is just like really, really small. But to nail that down, we should have the computer repeat that whole process all the way from the shuffling to the difference of proportions a lot of times. And so let's give that a try here. This code will do this for us. So we're going to run it right now and then explain parts of it a little bit more. So there's all that code, several lines of code, and we run all those commands. And it takes a little while, have to think about it. You see this little stop sign here for just a moment, it went away. And let's read what's in the console first. There's some technical stuff that we'll learn about more when we talk about tested significance, stuff like null distribution and test statistic, and things like that. But the key is they've done it a total of 1,000 times. 999 times they did it by repeating the experiment, uh, shuffling the constant situation, and then they had the one time where this the actual data is totaled 1,000 times. And you know what? Only one time out of all that did you get 30.8% or more. I mean, look at this. That the one time was the actual data. All those other times you were actually like less than that. And there's some warning messages that we won't go into. Over here, there's actually like a graph of the difference in these proportions, and most of the time you're getting around like a 0%. And it looks like sometimes you get around as high as a 20% and as low as a minus 20%. But the only time that you got, the only time you got, 30.81% or less was, like, I guess, was it just this once, maybe twice? You got that. So the chance, I'm thinking, is like about, there we go. The chance is basically like a 1 in 1,000 or less. So the p-value is very, very small. So back to the slides. Whenever you make R do something random, it's a good idea, if you don't want the random results to like keep changing on you every time you do them, to do what's called setting the seed for R's random number generator. And that's done with this little R function here, set.seed. And you can just stick any like whole number that you like inside those parentheses. And then every time you do all the random stuff, you'll come out with the same results. They'll be random looking results, but they'll be the same. You could get different random results if you just replaced with your own seed. Oops, what did I just do there? If you replace this with your own seed, then you would get a little bit different random results, but I bet you get the same small number of times that you ever get more than the 30.81%. Let's give this a try over in RStudio. So I'm going to copy in, but before I run, I'm going to change the 30/30 to, I don't know, how about 1, 2, 3, 4? And now go down and run. And again, it looks like we got a slightly different looking histogram here. We were getting slightly different results, but only once did we ever have a 30.81% or bigger difference. So I'm thinking that the p-value is very small, very close to 0. So think about this. If the null hypothesis is correct, there's almost no chance of getting a difference as big as the one that we saw in our experiment. So rather than believe that, I would believe that there is some relationship between the situation a person is in and the decision that they're liable to give. And since this was an experiment, that association really must be due to the explanatory variable causing the response variable. So I think we've got some pretty strong evidence here that people's decisions are based on the way the money is lost, that they're really caused by the way the money is lost, not just the amount of money that's lost. So just summarizing the whole two sections, 1.3 and 4 here. In an observational study, people come to the study with the values of the explanatory variables already determined. Researchers don't mess with that. They record the explanatory variable X, they observe the response variable Y. But in an experiment, researchers assign the values of X to subjects, hopefully using chance, so that the different treatment groups are as similar as possible, except in what treatment they're getting. And then they observe the response variable. And if they use chance to assign, then this inference question is always going to have this form: are the results due to the fact that the X variable causes the Y variable? Or was it just chance variation in the assignment of subjects to their groups? So that's it for now. We will dig deeper into some of this analyzing of data and looking for patterns in data that's being dealt with by some of the graphs that we've been making and some of the tally tables that we've been making. We're going to start delving into that more deeply in the next chapter. Until then, so long.